All right, thank you. All right, so I want to start off with a question. What is WASI? So if you've been following the space for a while, you've probably heard us use phrases like non-web WASM or WASM outside the browser. And these start to get what we're talking about. But they really aren't very precise at talking about kind of the WASI that's emerged as people have shown up and talked about the use cases they want to do with WASI. On one hand, non-web. Well, the web is actually more than browsers at this point. The web has grown way beyond just like HTML pages and hyperlinks. The web includes things like ActivityPub, Web of Things. These are W3C standards, part of the web. Like, there's things like WinterCG. So the web, in a sense, has grown beyond just browsers. It really represents like an ecosystem, an interconnected ecosystem of things that share values. Values about interoperability and having open standards. And it really seems like WASI can participate in that. WASI can fit in that environment very well. We want WASI to interoperate with web standards rather than compete with them. We want to have WASI interoperate with other platforms it integrates it to rather than compete with them. So we want to have the same values of interoperability and open standards. We have another phrase, which is WASM outside the browser. But there are a lot of people, including a lot of people I've talked to like at this conference, who actually want to run WASI programs in browsers. So WASM outside the browser doesn't really describe that use case either. So I'm going to put forward a phrase that I think makes a lot of sense. See if people like it. I think WASI wants to be a WASM native API ecosystem. So what do we mean by WASM native? And so we have WASM that's running in contexts where there's JavaScript, traceable in browsers and other things. And we have WASM running in places we call standalone, where it's just WASM. And so WASM native API ecosystem refers to having APIs that will work anywhere you have WASM, which might have JavaScript. It might not have JavaScript. It might have other things in the host. And WASM native also refers to really embracing the values that make WASM itself special, things like portability, sandboxing, and supporting multiple source languages. We want those things to be reflected in the API ecosystem as well. There's a lot of diversity in the API ecosystem right now. If you look at the WASM world, and especially like what people are doing at this conference, people are doing a lot of great things and experimenting in different directions, and that's really great. At the same time, we also have a kind of growing need for we need some more commonality. We have a lot of diversity. It's also starting to have a risk of fragmentation, of people are going in lots of different directions. We want to keep experiments going. We also want to start building up a commons of things that can work together, and not just APIs, but also the conventions and tooling around APIs. We can have some commonality across the ecosystem. And so the WASI vision for an API ecosystem has kind of two parts. One of them is a standards forum. So a standards forum, you have multiple stakeholders coming together. And so this part exists today. We have the WASI subgroup. The WASI subgroup is a subgroup of the WASM community group, which is the group that develops the WebAssembly standard itself, which is itself part of the W3C. So we're working here. We have quite a lot of people attend the meetings on a regular basis. They're open meetings. People are welcome to come to them. You just need to sign up for the W3C, and you're welcome to attend these meetings. At the same time, not every API needs to be standardized, developed in community. In the committee process, it's a lot of work to go through the committee process. Doesn't always make sense. And I think as WASI matures, I think we're not going to do as many things sort of like committee first. It's going to be more like people develop their own APIs, and then when they gain traction, then we're going to start standardizing those things retroactively, as opposed to a lot of what's happening right now where we're doing standards up front. I think there's reasons for it, because part of the work we're doing right now in standardizing things up front is to start building up this common set of vocabulary and conventions for how you make an API. What does it mean to design an API for WASM? What language do you write the description in? What are the conventions? How can we have things that, even if they aren't standard, can still fit with a coherent API ecosystem for WASM? And so all this raises a big question. What do we want? And when I say we here, I mean like everyone in this room and everyone in the broader WASM community. What do we want of our common ecosystem? This is the time to ask this question, right? We have to get this question and think about what do we want this to look like? What does the commons look like? talk about this question, I'm going to talk about a mystery. This mystery is the case of the missing Wasm. It was a dark and stormy night, and you're sitting in your room, and you're reading the Wasm core spec, and you finally get the math-extra vendor, and you're like, OK, this Wasm module thing is pretty cool. Right? So get these Wasm modules. This is a neat construct. Inside this core Wasm thing, it's like these modules, and they have these imports and exports. And the really remarkable thing about these Wasm modules is that there's no implicit sharing. All the sharing that happens between the Wasm module and stuff on the outside goes through these imports and exports. And the imports and exports have types, so they say exactly what's being shared. You know what the import is doing, you know what the export is doing, and there's nothing else going in and out. There's no shared namespace, there's no shared context, there's no shared registry, there's no shared address space. It's just like you get imports and exports. And this promises to be really powerful. This looks like the thing you could all you have to do is wire up imports to the exports of another module. You could snap these things together. It looks kind of like the system you could build a pretty powerful modular, Lego brick kind of experience of wiring up exports to imports. And you know that there's no kind of worry about, OK, is this going to conflict with that thing? Is there going to be some kind of implicit conflict between these two pieces? Is this going to work? You can largely ignore that stuff. We have this kind of system with no shared state. You can say, wire up your imports, your exports. The type system will make sure the types match. And we can have pretty good confidence that this will actually work. So we're going to have one Wasm module could link to another Wasm module, wire up imports and exports. But then we start looking at, OK, now we've read the core spec, and we're pretty excited about the Wasm thing. It's really great. And now we start looking at what compilers do in practice. How do compilers work? So one of the things that compilers do is they have to represent complex data structures. And Wasm's type system gives you numbers, and more numbers, and just 4 numbers. And that's all you get. So what do I do with all my other data structures? And so far, the answer that Wasm has is we have this thing called linear memory. So linear memory is this big array of bytes that we've specially optimized to work like an address space, be pretty efficient at it. And so we know what to do with linear memories, right? This is basically an address space. You can basically treat it like you do it in a C language or anything based on the C abstract machine model. We can lower all our data structures into these serialized byte forms, and we can have pointers into them. We can have structs. We can have arrays. We can do all the things in linear memory. But then when it comes time to link things together, what do you do? If you're going to pass a data structure off to someone else and it has pointers in it, they need to have your same memory to be able to resolve your pointers. You have your pointers into your memory. They can't resolve that without hitting your memory. So you have to export your entire linear memory. This is how a lot of Wasm toolchains work today. So you just export your entire linear memory, and then someone else you're being linked to, which could be the host or it could be another Wasm module, in order to work, has to import your linear memory. This is really tricky to do because either the other thing has its own memory, which means it also has to import your memory, and now it has 2 memories. And Wasm could do that now. We have multi-memories. So we can have 2 memories in the same module. But it's still tricky to do. Most toolchains aren't really set up to think about multiple address spaces very effectively. Most source languages don't really have the mechanisms to think about this kind of stuff. So it's really tricky to do that with multiple memories. And if you don't have your own memory, the other option is to say, I'm going to import the memory from the other module, and it doesn't have its own memory. It's just going to live in the existing memory that's going to share with the first module. That means they need to share everything. They need to share the malloc space. They need to share the stack space. They need to somehow have some kind of carefully coordinated thing to make sure they don't stomp on each other's memory. And that implies a very, very tight level of coupling between these things. They have to have a very, very close relationship to coordinate who's going to use what memory where, how are we going to coordinate what's being used and what's not being used. So this linear memory gets shared from one Wasm module to another Wasm module. That's how a lot of things work today. And once we build that, which is sort of the natural path we're on, the rest of this path kind of unfolds before us. We say, OK, we've been here before. Anyone who's worked on compilers or runtimes or DLLs or OS kernels, we've seen this story before. We know how this goes because this is what we do. This is how we connect things together in the systems programming world. We build ABIs. And so ABIs are this thing that Unix taught us long ago to do. You have your C header file. It defines an ABI, and the ABI becomes the interconnection point between all the things. The ABI is the ground truth for interoperability. The ABI is what really matters if you want to have a DLL, talk to another DLL. The ABI is what matters for your executable, can it run on this platform or not? And so we're all used to this. We're all kind of just like, we just accept it because this is how we've been doing things for literally 50 years or more. It's like we build ABIs, and the ABIs determine what we can and can't do and how we can evolve systems. And the ABIs kind of govern our intuitions for even how you design systems. They have a very, very deep influence over how we do things. But we also know in the back of our minds that ABIs have some dragons. Some monsters that are scary. They're hiding out there, and Wasm adds some of its own monsters. ABIs are error-prone. Raw pointers in these ABIs, right? So we're passing these things around. And it's one thing to have raw pointers in the context of like a C program where you can sort of blame a C programmer if they get it wrong. But if we're talking about linking together modules that might be written by different people in different programming languages and trying to make sure that everyone gets like, okay, make sure you don't use that pointer after it's been freed, it gets very complicated. And this is not a good situation to be in if we care about security. ABIs come with no isolation, right? We're exporting our entire linear memory. And when you do that, you're basically giving up everything else too, because once someone has control over your linear memory, they have control over everything you're doing, essentially. So there's basically no isolation in these ABI systems. We don't have this kind of nice property of there's just one thing being shared, my imports and exports. We're exporting everything. ABIs make thinking hard. This problem with, like, I'm exporting my memory, you have to import it somehow and deal with that. There are ways to make it work. In fact, we've been talking to some people here at the conference that managed to do this. But it is pretty tricky to get it right. ABIs make evolution hard, right? ABIs are notorious. We've seen this play out on all the places we've seen ABIs happen, that ABIs get baked into things. So we have like the Y2038 problem, where all these 32-bit Unix systems are stuck with a 32-bit timestamp that's going to overflow in the year 2038. And it's taking them decades that we've known about this problem to fix it, because the ABIs are baked in so hard, it's hard to you can't just overnight change a thing because you need to change everything at once. The way ABIs work is that you bake in all the low-level details into all the implementations and all the tool chains. So it's baked in all these places. It's possible to evolve ABIs, and there's kind of this art form that's been rising up over the years in this space of like how you can evolve ABIs over time, but you're kind of limited by the flexibility that you happen to have given yourself when you designed the ABI in the first place. So if you happen to have given yourself padding bytes, happen to give yourself, a struct length field or a version field somewhere, then you can have space to do certain things. But it takes a lot of foresight, and ABIs have a tendency to calcify. Even just adding new functions. This is like one of the things that you're supposed to, in this art form of how you evolve ABIs, adding a new function is one of the things you can do. But it's still hard to do. To add a new function, you need to, first of all, be really careful that you're going to get it right, because you're going to have to live with the thing forever. And second of all, you have to make sure that you really get it right, that in terms of like all the WASM engines are going to have to implement the same ABI, and then all the tool chains are going to implement it too, and they're all going to bake in all these details. And none of us is going to want to change it once it gets set up, so it's really difficult. There's a lot of overhead. Even adding a single new function takes a lot of work. Virtualization is hard, right? This is one of the really cool things about Wasm we're talking about, is like we can virtualize APIs, but when you have an ABI, it's not self-describing. It's just like, here's some pointers, and it's impossible to have tools that can automatically wrap these things and know what the semantics are, because we don't know what things like the memory semantics are. We just have to, it's a pointer pointing to something. I can't wrap that very easily unless I'm doing a wrapping by hand, and if I wrap by hand, I have to know how the ABI works. And then there's some really big points. I should make these bullet points bigger, but Wasm GC is coming. And Wasm GC and Wasm, this is where Wasm kind of throws in some new twists of these dragons we haven't seen before. In Wasm GC, it's not like GC in the native platforms, where GC is sort of running inside the address space. Here we have a GC that's outside the address space. The GC systems fundamentally don't have the linear memory. So when we have language like Kotlin and other languages that are coming along that are using Wasm GC, if we all bake in ABIs as the way we all talk to each other, what are those languages going to do? And you can say, well, maybe they could have like a linear memory that exists for the entire reason of talking to the ABI, and they have to like copy data into the memory and then copy it back out, and like it gets pretty complicated for them. And so there's a real risk that if we don't think of Wasm GC and think about how we're going to unify the ecosystem, we're going to end up with a split ecosystem. But the GC languages could all kind of do their own thing, have their own conventions, and the ABI languages can like do their own thing. We can end up with a fairly distinctly split ecosystem. I think that would be a bad outcome. I think it's worth thinking about the spirit of Wasm, thinking about interoperability and how Even as we add things like WASM memory64, which in the toolchain side we sometimes call WASM64, but at the WASM spec level, WASM64 is not a separate architecture. We just have WASM64 as a separate feature, but there's still just one WASM, right? We don't have a separate WASM32, WASM64. The only reason why WASM32, WASM64 as terms exist is because we're using toolchains that are kind of very obsessed with ABIs and very obsessed with the fact that 32-bit versus 64-bit means your pointer sizes are different, which means your ABIs are different, which for compilers like C compilers is a really big deal. And so we talk about this as being part of the architecture. So we have WASM32 and WASM64. But outside of that kind of context of C compilers, there's no such thing as WASM32. There's no such thing as WASM64. And even WASM GC is just, they're all just like different features within the same platform. And so when we talk about what do we want in a shared API ecosystem, I think what we want is a shared, across all the languages, API ecosystem, where everyone can participate equally. So what happened? Where did our WASM go? This WASM we had originally that was composable, and you could link things together without having to worry about the shared state. We have exported linear memory. We don't have any of this stuff anymore. It all went away. So where can we find it? Where can we get this WASM back? So we have some usual suspects. We have places we can go. Ideas that have come up first time. Memory views get suggested a bunch of places. I've even suggested myself at various points along the way to get to where we are today. And so the idea of a memory view is like, OK, so instead of exporting the entire linear memory, what if we just export parts of it? What if we have some kind of way, like a first-class value you can pass around, which is like a pointer and a length or something, and you can pass it to other people so they can get just a slice of your memory rather than giving the entire memory. And it does solve some of the problems. It does get to the point where we're not exporting the entire linear memory anymore, and we don't have to worry about what if you run off the bounds of what I meant to give you and you go into something that I didn't mean to give you. So it fixes those problems. But memory views don't solve all the problems. One of the problems is that within memory views, it's still, you're talking about bytes. You still have to have things like struct layouts and struct offsets still apply within these memory views. But there's also a problem with lifetimes. How do we make sure that the memory view, this thing that we passed out as a pointer and length, doesn't outlive the allocation in the memory, right? WASM semantics don't understand malloc and free, because those are just things that are like conventions you can do within your linear memory. So there's kind of no built-in knowledge of when you actually called free or realloc or anything else with these memories. So how do we make sure that that memory view we passed out doesn't outlive the allocation that it's pointing to? And similarly, how do we make sure like when the memory view is done, how do we notify the WASM program that like, OK, the memory is not being used anymore, you can go ahead and free it, instead of just like pinning it forever? So these are some complicated questions, and maybe it's possible to find answers to these things. But the memory views have another problem. They're not virtualizable. So with memory views, the idea is you interact with these things by doing loads and stores, right? Because it's just literally a view in memory. Loads and stores can't be intercepted. If we want to have virtualization, it means we want to be able to intercept all the operations you can do. That's sort of a key property of how virtualization works. And I think virtualization is worth it. It's a big thing, but being able to say across the ecosystem that every API is virtualizable is a superpower that we can have. And if we go down the path of memory views, we weaken that superpower because we'll have these things that can't be intercepted. We can have loads and stores. If you pass a view around, and a message can get sent through that can't be virtualized, that can't be intercepted, that can't be translated, that can't be monitored. All right, so in our like line of suspects here, Ms. Marple calls the next business, and it's protocols. So ABIs have the tendency to calcify, and they're hard to work with. And so there's kind of a common thing that comes out. People have figured out a way to solve this. It's like, what if we said, we'll just let the ABI calcify, and we're going to route new APIs as like a protocol on top of a fixed API. So you can imagine, even in the simplest case, you have like an API, which is like a byte stream. You have a way to read bytes and write bytes. We're say, we're going to encode, like every time you want to add a new function, instead of going out and doing all the hard work adding a new function to the ABI, we're just going to have a protocol by which you can like encode a function name or some other identifier, and then arguments you want to pass to it in the byte stream, and send that out and have it come back in. This could be encoded with like JSON or protobufs or flat buffers. There's lots of different like particular schemes you can use, but we can like pick one and say like we're going to have a protocol. But this doesn't get back to the missing WASM we had. This isn't back to the WASM where you could directly link things together. This is saying like the imports and exports no longer describe the APIs that a module uses. Because the actual APIs you're using are these sort of dynamic values that only exist at runtime, that can't be detected statically. One of WASM's big strengths people talk about a lot, one of the reasons why a lot of people are here, is the startup times. And one of the ways that WASM achieves these startup times is by having a static type checking system, a static validation. we can do a lot of work up front, not just the validation, but we can also do optimization up front and kind of like pre-bake in a lot of work so that in deployment time, we can start up these things very, very quickly. Moving things back to runtime takes away from that. Like the more dynamic runtime we have to do, dynamic encoding, dynamic type checking to make these protocols work, dynamic dispatch to make these protocols work, we weaken that advantage. And we step away from the spirit of WASM, which is like one of the big characteristic things of WASM is we have this static, ahead of time linear validation step. The next suspect is kind of a variation of the previous suspect. What about everything as a file? And I should be clear to talk about here, what I'm talking about is, there's different senses of everything as a file. What I'm talking about here is like, if you have some kind of new device, like even like traditionally in Unix, when they started saying like, okay, what's the first thing we do with everything as a file is we're looking at something very simple like a serial port. So a serial port is not a file. But Unix was able to say a serial port can act like a file in some ways. Now that's a little tricky because some file operations don't make sense for serial ports, right? You can resize a file. You can fsync a file. You can't resize a serial port. That just doesn't make sense. You can't fsync a serial port. These are things that don't make sense to the serial port. And the serial port has operations that don't make sense for files. Like you can set the speed, or you can set handshaking parameters and other things like that in serial ports. And so like they both have operations you can't do in the other. So if we coerce serial ports to acting like files, what we're essentially doing is saying like there has to be some kind of protocol or some kind of like convention for how we're going to encode the serial port things on top of the file API and send it through. And then as we take this further, people add more kinds of devices, and it just becomes like we're going to have more and more protocols. And literally, if you look at systems like Plan 9, some of what they're doing is like literally just having device files that you write string commands into, ASCII string commands into, that then the OS will then, or the other side of it, whatever it is, will then parse and then dispatch into the actual function. So we're essentially like bypassing this static function mechanism using a dynamic function dispatch mechanism. So we're just like layering an extra layer on top with the dynamic dispatch system. And if we really step back and think about this, what are we really solving with these systems? And we're solving the problem that adding new functions is hard. But that was the thing that came from ABIs. ABIs are where they got this problem. ABIs are the reason why we're doing this, because we think that adding new functions is hard, so we think that we can't add new functions, so we think that we'll just have a fixed set of functions, and then build a new layer on top of that we can run over at runtime. If we follow this path to its logical conclusion, we end up with a dynamic system that's much more dynamic and harder to optimize ahead of time. So here's where the component model enters the story. The component model gives us some new tools for thinking about these problems. And one of these new tools, it's not really a new tool. In fact, it's been used quite widely in a lot of spaces, like OpenAPI and other places using in like protobufs and stuff like that, is the IDL, Interface Description Language. And thinking about this in the context of WASM, it really stands in pretty sharp contrast to the ABI-oriented approach. We have pretty distinct approaches. So ABIs, we're always talking about things like pointers, memory layouts, struct offsets, lifetimes, bake details into all of the engines and all the tool chains. Everyone has to bake in the same details, and it works. If you have different details, then like things break and demon-file your nodes, and it's bad. Adding functions is hard in ABIs. That's this core intuition that we have built up on top of this thing that comes from ABIs. And it makes tunneling protocols on top of ABI-based protocols look really attractive, because like this gives us all this flexibility that we're missing from the ABIs. But the contrasting approach is IDLs, and in particular the Wit IDL in the component model. So what does this give us? It gives us a different way of approaching the problem. Instead of saying we're going to sit down and the first thing we do with an ABI is we're going to write a huge mountain of code that's going to do the ABI and bake all in all details. In the IDL world, the first thing we do is we sit down and we write binding generators. So we say we're not going to write ABI code by hand for every single API, because if you look at WASI, it's getting pretty big. There's lots of things in there. We don't want to have to spend a lot of time every time someone proposes a new API and someone wants to implement it, someone wants to play with it. We don't want to spend all the time adding ABI code to do all this stuff. We want to be able to auto-generate these things from a high-level description. So the Wit IDL, the tooling that comes with that, gives us the ability to do that. Binding generators, what we have today, protocol generators are coming. IDLs give us ergonomic API design. They give us high-level types to describe the intention of the API. Right? Char star doesn't tell you what it's doing, but string says, this is a string. Right? In C, you can sort of use to like, oh, char star just usually means a string. Or if we have like a char star and a usize, size t, whatever you want to call it, pair, like people that are kind of used to APIs kind of recognize what that means. It's probably the length of the array. But in the IDL, we have a type like list. It's literally like list of a type of thing that you want to have a list of. And the details of exactly how we're going to transfer those things around, how we're going to represent them in different source languages would have different ways of representing things, can be handled by the tool. So we don't bake in the ABI, we bake in this high-level type system. And the high-level type system becomes the source of truth for interoperability, not the ABI. So we're still going to have ABIs, but ABIs kind of shift to becoming, instead of the external source of truth, the internal interface to the type system. And then when we link things together, we don't have to say that the connection point between one piece of software and another piece of software is like a machine jump instruction. You have to set everything up in memory just right so that when you jump across the boundary, the other thing can like start running and it all kind of like lines up where it's expected to be. That's kind of like the calling convention way of doing things. We can say, like, I'm going to call you, and I have this high-level set of types, and you have that high-level set of things inside. And the Wasm runtime can understand that. It can look at your ABI, and it can say, OK, we want to pass a string. Well, maybe one side has a UTF-8 string, the other has a UTF-16 string. And the runtime can see that and say, the way I link you is not going to be a simple jump. It's going to be, there's going to be a bit of stub code that's going to do some transcoding, like transcode from UTF-8 to U16. And so we can transparently link things, even if they have different string representations. And this generalizes to all kinds of different data structures. You have different list representations. You have different ways of doing result types. How do you do error handling? We can have high-level types that can handle this. So this also gives us a path to sorting more source languages, because we're also not baking in the representation for things like, oh, it's a pointer length. But what if it's GC? Then we don't have a pointer. It's like a GC array, right? Or the result type is another thing. Like if you have a result type which captures the semantics of success and failure in a result type in Wit, which if you have JavaScript, the failure type can map to a JavaScript exception, and the success type can be the return value. If you have C, we can use, like the convention in C for error handling is you have a return value that indicates success or failure. We can map to that. If you have Rust has result types. You can map result type to result type. But any language has a way of, like, idiomatic way of handling errors, and having a high-level result type in the IDL lets us map to every single source language's idiomatic way of handling errors, so we can get this kind of interoperability with this kind of intent of saying, this isn't just any old return value. This isn't just an int which just happens to have error no codes in it. This is a result which, in the type system level, declares, I have two things. I have a success value and a failure value. And so tools can be generated to generate wrappers around that, and bindings for that can automatically handle those in idiomatic ways. This is one of the big ways that we can take WASI beyond just being like this C-level ABI thing, thinking about low-level system calls, and really make it more accessible, directly accessible to a lot more source languages. This also gives us better virtualization and composition. As we have tools that can generate wrappers that know what's going on, they can generate smarter bindings and more bindings to do things automatically. And this is one of the big ways we can get out of the rigidity of ABIs, because if something is wrong, even if you get your API, your Wit IDL, if we decide later on we want to add a parameter or something, or even take away a parameter, or change the order of things, like, we can do things, and if there is a mismatch between different things, we'll have enough high-level type information that we can auto-generate most of the work of adapting from one thing to another thing. So we actually have a pretty clear path to evolving. And when we have this pretty clear path to evolving things, like we can add functions, we can change functions, and we have enough self-describing things, adding functions becomes easy. If you want to have a serial port API, we can just talk about serial ports. We don't have to talk about how do I encode serial port operations within file APIs or within ioctl parameters or whatever. We can say, let's just talk about the serial port functions. We have things like set speed and that kind of thing for serial ports. We just add new functions. We don't have to worry about, oh my goodness, it's going to be so much work to go to all the source languages and if I manually add a function to call the set serial function, set the speed function in, here's one for Rust, here's one for Go, here's one for TypeScript. Let's go all these tool chains, it's going to be so much work. But in an IDL world, what does this look like? It looks like you write an IDL, you write your Wit that has a function in it, and then you distribute that, and all the source languages can then run the generator to generate their bindings, and you're done. They get the bindings in their idiomatic source languages, and you don't have to do this sort of implement the ABI everywhere work. This radically changes kind of our perspective, and it really makes us look differently at these kind of solutions about let's tunnel ABI or tunnel protocols over ABIs. What if we just make it easy to evolve the APIs themselves? All right. Do engines have to implement all WASI interfaces? A question that I get a lot, and the answer is no. WASI has a lot of APIs these days, but we have this mechanism in the component model called worlds. And so worlds really serve as the meeting point between engines, what they implement, and what developers can target. The worlds can determine, like, here's a subset of all the APIs that make sense for a particular use case, and engines can target those worlds. And then developers can target those worlds and know what's available in those worlds. All right, I'm almost done. I'm almost at the demo. So here's a quick view of the WASI roadmap. This isn't absolutely set in stone anywhere, but this is a thing that I've presented to the WASI subgroup and gotten pretty good consensus there, that this is a good path forward. So in particular, what's happening here. So Preview1 is the version of WASI that's kind of out there right now. It's being used in a lot of different tool chains. It's implemented in a lot of engines. It's pretty POSIX-like, comes from Cloud ABI. One of the notable features in it is it does have director capabilities, which is a little bit different than POSIX, kind of taking a step towards the direction that WASI as a whole is heading in. And so the focus right now for Preview1, it's not based on the Wit IDL. And so the focus right now is, like, we really want to, like, it's being used in all places. We want to support those existing use cases. So there's not a lot of documentation for Preview1 right now. And so we're working on adding documentation in the places where people have confusion. There's not a lot of tests. We're working on adding tests, and we're really just working on supporting those existing use cases rather than, like, adding new features to it. Because the new feature work is going into Preview2 at this point. So Preview2, the big headline is we're going to rebase on the Wit IDL and the component model, for the reasons we just talked about. And we're also taking this opportunity to fix various bugs. If you ever had to do FD redir in WASI Preview1, you have my condolences. We're fixing it in Preview2. It's going to be much simpler to do directory APIs in Preview2. So various things like that we're fixing based on experience from Preview1. And the big headline feature, as far as adding things, is going to be sockets. And I'll show a demo of that in just a minute. Beyond Preview2, we think it makes sense to have one more preview. Preview3 is when we added the integrated async coming in the component model. And so if you saw Tyler's talk from yesterday, where there's this design for how async can work and how we can combine async in multiple languages together on a single event loop. It's pretty exciting stuff, and I think that makes sense for Preview3 to make sure we can integrate that kind of async into the WASI as a whole. And beyond that, it seems like we're kind of done with previews at that point. We can start talking about WASI 1.0. When we get there, we'll start some conversations with the Wasm CG. Those conversations haven't happened yet. We don't exactly know what that looked like yet. But WASI 1.0 is like, that feels like the time when we can start talking about a real standard that could live for a long time. And at each of these steps, these are chances for us to incorporate feedback from implementers. Right? As WASI grows, we'll get more feedback in more places, more use cases, and we'll get more feedback. We'll incorporate them into Preview3, incorporate them in WASI 1.0. And even beyond WASI 1.0, we have WASI 2.0. And this property of being able to virtualize APIs and implement an older version of an API in terms of a newer version will give us a lot of flexibility to evolve things even after we've standardized them. All right, now let's get to the demo. So I have a URL if you want to check out the code. It's all up online here. Switch to my window here. So I'm going to run cargo component build. Cargo component I should show the whole thing here. So cargo component is this tool we have for building a component within the cargo system. So you have, within your cargo.toml, you can describe your component dependencies. I don't have time to dive into it right now. But the kind of idea is, like, this is the tool for Rust, but it also kind of shows the path for, like, other languages could follow. So if you have JavaScript, you could do a similar thing with the package.json file, and other systems have their own build systems. And the idea is, like, maybe you could incorporate building components into these things, so it's relatively natural for developers to use, rather than having components be this, like, separate tooling you have to pull in. It could just be built in, like, a fairly regular part of your regular tooling. So we built this thing as a server. Yes. Apparently you can't see my screen. I had not anticipated this. Is this possible to fix? I don't know if I can fix this right now. Unfortunately, you can't see the demo, but if you can believe me. So I have cargo component. It's a cargo component build, and I'm building this program called Echo Server. And it's a fairly simple program that's using Preview2 APIs that are using new socket APIs to open up a connection, or open up the socket and listen on it on localhost. And then I have another program called Echo Client, which you tell it the port number that the server printed out, and then you run the client and connect to the server. So I'm really, I apologize for not having a demo you can see on the screen here. That'd be super fun. But maybe if you take the presentation out of full screen. I can try that. So now, do I have to, like, there we go. All right. So This window here is server. There we go. All right, we're back online here. This window here is the client. So here I did my cargo build. I made the server. And now I have a program called host, which is just a fairly simplistic program that links in Wasm Time as the engine and links in the host implementation of Preview2 that we've been developing. Me and various others are working together on this. So if we run host on this Wasm component that we just built, so this is a component. It's running the server. It's listening on this port 36613. So now here, I'm going to run cargo component build. It's going to make a component. And so this, the client is just, it's going to connect. It's going to send a message across. The server is going to echo it back. And we can run it and pass it the port number, 36613. And there we go. You can see the bottom of that screen here. So, very basic socket demo. In historical terms, nothing fancy. That we did a socket and had a client collect it. Like we've been able to do this for I don't know how many 50 years now at this point in Unix, maybe 40. But basically, this shows you that like sockets are part of the story here, and they work. We have them implemented in our Preview2 implementation for the prototype we're building, and they're definitely part of the story here. We don't yet have like the standard library support wired up for things yet, so you can't do like in WASI, you can't do stdnet yet, but that's where we're going. So we'll get those things wired up on other languages as well. And with that, back to my presentation, hopefully. I don't know how to bring the presentation back, but that's all I got. Thanks a lot.
Hi, great talk, very interesting to see. Here.
Right, okay.
Yeah. You started by mentioning that, for example, sharing pointers into data structures is one of the big problems, but is this solved now, or how can I share views for memory?
In a component model, the main way to share memory is to use a feature called resources. I didn't have time to go into the resources in this talk, but basically what a resource is, it can be either like a host resource, like literally an OS or other kind of external resource, like an I/O thing, or it can just be a data structure in memory. And then with resources, the way you can use them is you get handles, which are essentially just pointers, and you can pass these handles around for other things. And that's effectively a form of shared memory, because you have memory, you're passing pointer onto it. The difference between resources and like traditional shared memory is that with resources, there's no direct load and store. All the access to the resource goes through function calls, and the function calls are guided by the type of the resource. So you have a way to do this, and it can even be efficient, because these function calls are just calls. We can inline them, especially at instantiation time where we know the function calls are going. So we can get efficient things there, but it's not direct loads and stores. So it does require, in many cases, like rethinking about how things are working. I should also mention, people have asked me a lot about mmap over the last 2 days. And so there is potentially a path that people have been talking about if we had like a blob resource, which we could imagine be like this very large database blob or whatever, and we wanted to like mmap parts of that blob into the Wasm linear memory. That's potentially possible. There's a possible path where we could do it. And we could do it without having to add I/O semantics into linear memory, which is a pretty scary thing from like the abstract Wasm semantics perspective. So the way we might do it is we could say, if we have an operation which is logically copy all the data, or data in a range from a blob into linear memory, and then we have another operation which might be like copy it back when I'm done writing to it, and maybe another operation which is like now set it all to zeros. And so if we have these operations, these can pretty directly map onto like, oh, mmap from the blob into my linear memory, and then when I'm done, I can maybe like msync it back, or I can munmap it to get it out of my address space when I'm done with it. So there's definitely a path where we can have the fast mmap behavior to an outside resource in memory, where your program can very conveniently do loads and stores on it, in a way that we can rationalize with the semantics of saying it's just still a copy semantics. It's not actually giving I/O semantics to memory in the abstract machine. That's kind of a brief overview of some of the things that are possible in that space.
So these resources are like file descriptors plus some functions.
Yes. So in fact, resources are what we're using to model things like actual files, like the file handle will literally be like a file handle, and then in the C bindings to that, we'll have these things which we'll call file descriptors, which are the indices into the file handle table. But resources can be like an external thing, like a file. They could also be like just a data structure in memory. Like you can have resources, if you have like a virtualized file system, you might have an in-memory thing that might be in linear memory. Those could be resources that are accessed by handles by another component as well.
All right. First off, thanks for the talk. I have a question, because there's one thing that's changed between like Preview 1 and today, is that there's been this recent huge spike in interest from the kind of like container community and the features that they're used to, and then mapping them into WASI land. And do you expect those things to impact like WASI CLI? One of the things, for example, is Docker has like a workdir concept, and right now you can't actually say what the working directory is for WASI. Like, is it too late to address some of those things while everybody's like excited? Or can we get things like that in?
It's not too late. I think working directory is, I think the best answer right now is just something that like I personally have not really thought about. But I think we can add it. Really the trick here is to add these new features and give ourselves as much compatibility as we can in a way that doesn't affect the kind of core system. So we want to think about POSIX compatibility as like we want to provide as much as we can, but we also want to keep it isolated, like keep it at arm's length, so we can kind of preserve this core thing. There's a risk that if we go off and specialize too much for POSIX, that we could end up forking the ecosystem again. Like this is one of the big risks of like we could fork over Wasm GC versus ABIs. We could also fork over like, let's do all the POSIX things versus the things that POSIX doesn't work for at all. And we have to end up going about separate ways for that. I actually think that we can keep it together. We can keep the values of a unified ecosystem if we think in terms of POSIX compatibility as being a layer on top. Now, current working directory is just the thing that's not addressed by the current system, but I think there's actually an issue about it in WASI file system right now that I don't think we've responded to yet. I haven't responded to it. But I think it's definitely in scope of something we can fix in the Preview 2 timeframe.
Yeah, so you mentioned that the component model defines stuff like abstract lists and maps. But ultimately, they need to be mapped to language-specific implementations, right?
That's right.
Is this going to be implemented as part of the runtime that provides different primitives that are closer to what languages expect, or is it fully the responsibility of language compilers to target those abstract data types?
It's kind of split. There's a piece of it which is going to be in the bindings, the generated bindings, which will be specialized for a particular source language. So if you're generating binding for JavaScript, you're going to have code that's going to know how to construct a JavaScript dictionary, or there's a JavaScript column dictionaries and maps, I always forget. But the code to construct the JavaScript data structures, whatever they are, right? And then you'll have the component model side of it is like the abstract side of talking about, essentially like, let's enumerate the elements of the list in a way that the component model can understand and can generate like an adapter function which could be JITted. But then it has to hand off to like, it has to delegate to the code inside the component to say, okay, now I'm giving you these abstract list elements. I want you to put these in the list that you have, that you're building for your own source language. So it's like a split thing. In the middle, we have this abstract thing, which is source language independent. And on the inside of the component, we have the source dependent part.
Very interesting, thanks.
Yep. Sorry? We have to cut here. Thanks a lot. I'll be around for questions. If you have questions, I'll be out in the lobby.